Hi everyone, today we are going to continue on with our discussion about work and energy, and today we're going to talk about something called the dot product. And the dot product is a product between two vectors. In the case of our work, it's going to be the dot product between the force and the displacement vector. Some of you guys might already be a little bit comfortable with dot product. You might have seen it in another math class. But I'm just going to assume you guys have never seen this before, so we're going to kind of take it a little slow. So if you maybe are already familiar with the dot product and how to do it, you can fast forward to the examples. But we're going to cover two main questions in this PowerPoint. The first one is, what is the dot product, and how can we use the dot product to calculate work? Alright, so the dot product is sometimes defined as the scalar product. So whenever you're taking the dot product between two vectors, you end up with a scalar, which is what work is. Work is a scalar quantity. This whole process, like I just mentioned, is sometimes called the scalar product as opposed to the dot product. So if we have these two vectors here, A and B, and we wanted to get the dot product of them, that would be equal to the magnitude of the vectors times the cosine of the angle between them. And remember that when we're talking about these vectors here, we're talking about vectors with ijk components. So here's a couple of dot product properties or rules. If A and B are perpendicular to one another, then the dot product between the two of them is going to be equal to 0. Remember, if they're perpendicular to one another, that means that the angle between them is 90 degrees, so that makes the dot product between them be 0. So if A and B are parallel, then the dot product between those two vectors is just the magnitude of those two vectors multiplied together. And then if you take the dot product of a vector with itself, you get its magnitude squared. So, sorry that funky font happened right there. But since vector components I and j and I and k are perpendicular to one another, their dot products will cancel out, and you'll essentially just end up multiplying like components together. And that might sound a little bit confusing right now, but hopefully once we do an example, it'll all become a little bit clear. So, let's look at these two vectors, and this is not a not a force and distance and work example. This is just a generic vector example. But let's say we have these two vectors, and I wanted you to find the angle between them. We can use our dot product to help us do that. So, let me get my pen ready. Ooh, I accidentally fast forwarded. Sorry. No! Go back. Alright, there we go. Sorry about that. Let me get some white ink here. Alright, so we know that the dot product between A and B is going to be equal to the magnitude times the cosine between those two vectors. So the question wants us to find this angle, so that means that cosine of the angle between these two vectors is going to be equal to dot product of them divided by their magnitudes multiplied together. So the first thing we have to do is to find A dot B. Alright, so I told you guys before that the dot product of the components that are perpendicular to one another are 0. So what you have here is you have a component in the x direction, component in the x direction, component in the y direction, component in the y direction. So essentially, you're going to do multiply those components together. Because the component of this x direction multiplied by this y direction, since they're perpendicular to each other, that's just going to end up being 0. So, for our problem here, we have 10 times 5 plus 4 times negative 8 and this is 50, and then that is 32, so that is 18. And if we wanted to put units with this, since our vector is a meter, then our unit for this is meters squared, because this is a meter and this is a meter. So it ends up being 18 meters squared for the dot product. So now we need to find the magnitudes of the vectors, A and B. And you're going to do that using this rule right here. So let's look at A first. A dot A is going to give us A squared, or our magnitude. And we get that from doing little Pythagorean here. So this case is 10 squared plus 4 squared. So our A value is equal to the square root of 116, which is 10.8. So this is the magnitude of vector A. Let's look at finding the magnitude of vector B. We're going to do the same thing. Dot product between a vector and itself is going to give us the magnitude. So in this case, we've got 5 squared plus negative 8 squared, which is 64 plus 25, 89, square root of 89, which is 9.4. All right, so now we're going to put all of that together. I'm going to erase this bit right here. We have our magnitude of B, which is 9.4. We have our dot product between A and B, which is 18. And then we have our magnitude of vector A, which is 10.8. So now we have cosine theta. We're going to use this expression right here. Dot product, which is 18 meters squared, over the magnitude of A times the magnitude of B. So magnitude of A is 10.8, magnitude of B is 9.4. That gets us let me do this real fast in my calculator. So when we multiply those two numbers on the bottom together, we get 0.18 as the cosine of our angle. So we can inverse cosine that, and we get our angle to be about 80 degrees. Okay, so now let's take a look at how to use dot product if you're dealing with vectors for your force and your displacement. So now we're actually going to use our dot product to find our work. So particle is given a displacement vector of change in s as 2mi minus 5mj, and then a force is acting on the object during this displacement of 5ni plus 8nj. So find the work done by the force and the component of the force in the direction of the displacement. Alright, so work is equal to the dot product between the force vector and the displacement vector, right? Because work is a scalar quantity, so if I find the dot product between these two vectors, it'll give me my work. So in that case, work is going to be equal to the force in the x direction times the displacement in the x direction plus the force in the y direction times the displacement in the y direction. So let's do that part first and figure out what our work is going to be, and then we can figure out the other part of our problem. So we have 2 times 5 plus 8 times negative 5. And we're going to end up with a scalar quantity. This is 10 and this is negative 40, so our work is negative 30 Newton newtons times meters, or joules, however you choose to write that. All right, so the next part, we know that work is equal to force vector dot product of the displacement vector, which is equal to all of this fun stuff we just did. Which is also equal to that, Fs cosine theta. So we already know our work is going to be negative 30. So if I want to find the force in the direction of my displacement, if I rearrange this with my work, it's going to equal to work divided by the magnitude of my displacement vector. Now if I do this, this is going to give me my force that's acting in the same direction as my displacement. So in this case, our work is already solved for. We have negative 30. Now our displacement vector here, remember we want to find the magnitude of this vector. So that means that we have to do our Pythagorean here with our vector components. So that ends up being the square root of 29. So we end up doing 30 divided by the square root of 29 to find the force that's acting in that direction. Which we get about 5.6 newtons negative. And the negative sign makes sense because the object is experiencing negative work. So the component of the force that's creating that negative work, of course, is going to be a negative number. All right, so that is going to be it as far as examples are concerned. I know this slide says power, but don't pay attention to it. I just wanted to recap for you guys. So whenever we do the dot product between two vectors, what we're actually doing is taking the magnitude of those two vectors and multiplying them by the cosine of the angle between them. So another way to talk about this is to say this. If you're given vector components, you want to multiply the components together. You can do it this way as well, which is how we did the first example, and also how we did the second one. So we're going to get some more practice with dot product in class. I just wanted to introduce the idea to you guys, and I will talk to you all later.